Hello, and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at the concepts of stationarity and ergodicity. Yeah, I know, that's a funny word. I didn't make it up. But we will nevertheless talk about what it means for a random process to be perhaps stationary and perhaps even ergodic. We'll begin by talking about stationarity. Alright. A strictly stationary random process is characterized as follows. A strictly stationary random process has the following characteristics. First of all, the first order probability density function is not a function of time. And that would imply that things like the mean squared, the variance for that random process are also independent of time. The second order probability density function is going to be a function of only a difference parameter, tau, which is T2 minus T1. The second order probability density function is only a function of a difference parameter, tau, which is T2 minus T1. All higher order probability density functions are also functions of only time difference parameters. Okay? All right. We're not going to, in most cases, consider anything above second order statistics. So we're going to introduce another concept called wide sense stationary. Wide sense stationary means first order PDF is independent of time. The second order PDF is only a function of tau. And all of the higher order stuff we either don't know about or don't care about. All right? The higher order PDFs could be a complete mystery to us. We don't care about them. We don't talk about them. Or they may not all be independent. They may not all be function of only time differences. So don't know. Or care. Don't know or don't care about higher order PDFs. Good news is, wide sense stationary processes are what we're going to consider for the rest of the semester. This is us. Wide sense stationary. All right? Our random process that we talked about in the past couple of video lectures, if x of t equals a cosine omega naught t plus a random phase theta, my theta here is a random variable that's uniform on 2 pi. This is at least wide sense stationary. And we'll examine that a little bit more through some examples a little later on. All right, this is at least wide sense stationary. Frankly, I don't have any idea what the third, fourth, fifth, or higher order probability density functions look like. They may or may not be functions of only time differences. I just don't know, and really I don't care. As another example, the temperature outside of your home is not a stationary process. All right, we all know that the temperature changes throughout the day, right? We all know that the temperature changes throughout the day. The temperature outside your house is not stationary at all. All right, well, for stationary random processes, that means some of the statistical descriptions of our random process remain constant with time. That means that it becomes reasonable for us to start thinking about time averaging. Time averages. Time averages only apply to stationary random processes, or at least wide sense stationary random processes. All right? Time averaging only has meaning for at least wide sense stationary random processes. So for example, if you watch the weather report at night, the weatherman will tell you the overnight low and the mid-afternoon high. He might give you historical high temperatures and historical lows and things like that, but never once has a weatherman who is in his right mind told you the average temperature for a day. It makes no sense. We know it's colder in the morning than it is in the middle of the afternoon. Weathermen don't talk about average temperatures across a day, and the reason they don't do that is because it's a non-stationary random process. All right. Time averages. We're going to look at 3 of them, really. This is the time averaged mean. All right, that is the time averaged mean. So hopefully you remember how to do time averaging. I take a time domain function and I integrate over some temporal window, divide by the width of that temporal window, and then I'll let that window get arbitrarily large. That's what we're doing here. We take our time domain function, we integrate over a window. Here my window is 2t wide, 2 capital T wide. I divide by the width of my temporal window, and ultimately I'll let that window get arbitrarily large. That's how I do time averaging. Okay? I can have a time averaged mean square, and this will be the limit as t approaches infinity, 1 over 2t, integral from minus t to t, x squared of t dt. This is the time averaged mean squared. Okay, that's the time averaged mean squared. And we're also going to be interested in the autocorrelation. The autocorrelation is a second order statistic, and for at least wide sense stationary random processes, my probability density function is a function of only a time difference parameter. So my autocorrelation is always going to be a function of a time difference parameter, and that is the time average of x of t plus tau, and this is limit as t approaches infinity, 1 over 2t integral minus t to t x of t plus tau dt. All right, this is the time averaged autocorrelation. All right, so I guess I need to define some of my symbols here. My pointy brackets indicate time averaging. All right. Previously, we've talked about the expected value of a random process. I'm now going to introduce a little bit new symbology, and I'm going to say x of t with a bar over across it, and that will imply ensemble averaging. Okay? All right. Let me say a couple more things here. Notice a couple of things. One, if I take my autocorrelation and evaluate it at 0, I get my time averaged mean squared. And I know that my time averaged, or I know that my mean squared value is my normalized power. All right, and another thing, not all random processes are periodic, but if they are periodic, if x of t is periodic, then we can find our average over one period, and it's true for all time. If x of t is periodic, then we can do our time average integrations. Okay? So, for example, if we wanted to find the time averaged mean for a periodic random process, if we assume that x of t is a periodic random process, then the time averaged mean is just 1 over t integral from minus t over 2 to t over 2 x of t dt. And in this case, capital T is the period of x of t. Wasn't necessarily, capital T wasn't necessarily a period on the previous page. It was just a half of the temporal width. Okay? All right. So if we have a random process that is at least wide sense stationary, it makes sense for us to now start thinking about time averaging. Previously, we've talked about averaging across the ensemble. Remember, when I sketch out sample functions, I stack them on top of one another. Ensemble averaging is averaging across the ensemble. Time averaging is averaging along the time axis. Well, let's introduce a new word, ergodic. Let's talk about what it means for a random process to be wide sense, strictly ergodic, or strict sense a strict sense ergodic random process. First, it has to be stationary. Must be strict sense stationary. All right? For a random process to be strict sense ergodic, then the random process must first be strict sense stationary. And what that means is that all ensemble and corresponding time averages are the same. Right? All ensemble averages and corresponding time averages are equal to one another. So if I find the ensemble mean, it equals the time average mean. The ensemble variance equals the time average variance. The ensemble averaged autocorrelation equals the time averaged autocorrelation, etc., etc., etc. All right. Wide sense ergodic implies, first of all, that x of t is at least wide sense stationary, and the first and second order statistics are identical whether they were found through ensemble averaging or time averaging. Okay? So a wide sense ergodic random process is one that is first, at least, wide sense stationary, and the first and second order statistics can be found either through time averaging or ensemble averaging, and if I do them, they're identical. All right? Here's some really good news for us. Most, not all, but many random processes that you are going to encounter as electrical engineers are going to be at least wide sense ergodic. All right? Most random processes that you are likely to encounter in your career are going to be at least wide sense ergodic. All right. So I've told you in the past that we are only going to consider up to second order statistics for this course. And most things that we're going to look at are going to be at least wide sense ergodic. So from this point forward, if I say something is ergodic or if I say something is stationary, I'm implying that it's at least wide sense stationary or wide sense ergodic. All right, I'm just going to drop the wide sense stuff. Okay? All right. Well, let's do some examples. Let's look at our handy-dandy phase noise random process. There's my handy-dandy random process, which is created by embedding a random variable inside of a time domain function. My phase is going to be uniform on 0 to 2 pi. It's going to be a random variable uniform on 0 to 2 pi. It turns out that this random process is at least wide sense ergodic. Okay, and what we're going to do is we are going to find the time averaged mean and the time averaged autocorrelation. And we'll see that it was exactly the same as what we found in the previous lecture. So, time averaged mean. Time average mean, and by the way, this is periodic, so we can do our time averaging over only one period. This is going to be 1 over t, integral from negative t over 2, then t over 2, a cosine omega naught t plus theta dt, where my period in this case is 2 pi over the frequency omega naught. Well, hopefully you recognize that if I integrate any sinusoid, cosine function or a sine function, if I integrate any sinusoid over a full period, it's half the time positive, it's half the time negative, and that integral is exactly 0. All right? And that equals what we found last time through ensemble averaging. We showed that the ensemble average mean was exactly 0 and the time average mean is exactly 0. So this is sort of a proof by example that this particular random process is wide sense ergodic. It's not a strictly rigorous proof, but proof by example. Points in the right direction. Next thing we're going to do is we're going to look at the time averaged autocorrelation. That's that. And I'm going to plug everything in, and I get the following. All right, and I'm going to use the following identity. use that identity and move to the next page to proceed. A squared over 2t, integral from minus t over 2 to t over 2, cosine omega naught tau plus cosine 2 omega naught t plus omega naught tau plus 2 theta dt. All right. Well, notice that this portion of my integral right there, that is not a function of time t. My second piece of my integral right here integrates over 2 full cycles. That's integrated over 2 full cycles, and so integrates to 0. All right, so continuing on, we get an a squared over 2t cosine omega naught tau, integral from minus t over 2 to t over 2 of 1 dt. And then my result is a squared over 2 cosine omega naught tau. And this is identical to the result when we did ensemble averaging. All right, so that, strictly speaking, is not full rigorous proof that this particular random process is at least wide-sense ergodic, but it is. Okay? All right, so that's a quick introduction to the concepts of stationarity and ergodicity. Stationarity means that or at least wide-sense stationarity means that my statistics, first and second order statistics, are not functions of time. That means that time averaging starts to make sense. A wide-sense ergodic random process is one for which the first and second order statistics can be found through either time integration or ensemble averaging. All right, that's all for today. As usual, if you have any questions, please do contact me at your earliest convenience, and I'll answer any and all questions as fully and quickly as I am able. Have a nice day. Bye-bye.